Hello, everyone. Today I'm very happy to share my research about software stack design for quantum computing. First, a little bit about myself. I'm currently assistant professor at Electrical and Computer Engineering department. My research is on quantum computing. I work on circuit compilation, algorithm optimization, error correction and mitigation, and benchmarking quantum systems and algorithms. This semester, I'm teaching one course called Engineering Analysis and Computation. In next semester, I plan to open my new course talking about my research, which is called Special Topic Quantum Computing Systems. If your students are interested in quantum computing, please motivate your students to join my course. I obtained my Ph.D. at University of Montpellier in France, and I did my postdoc at Berkeley Lab. My office is at HEC 414, so you are very welcome to drop by and let's have a chat. You can also send me an email. So now let's get started. So what is quantum computing? Very roughly speaking, we can think of it as performing some computation based on the quantum hardware, which works according to the principle of quantum mechanics. The computational unit of quantum computing is called a quantum bit. We also call it a qubit, which has the unique quantum properties such as superposition, entanglement, and interference. The qubit can be realized in various physical platforms. The popular ones are superconducting qubits, trapped ions, neutral atoms, and photonic chips. So far, there is no conclusion to tell us which is the best quantum platform. The good thing about quantum computing is that if you design your algorithm carefully, we can leverage massive parallelism to achieve significant speedup compared with the classical algorithms. But quantum computing can only be beneficial for some specific applications. We don't want to replace the classical computers by quantum computers. They should work alone and solve some complex problems together. Quantum hardware has made great progress in recent years. This figure shows the roadmap from IBM to build their quantum computers. They plan to build a quantum chip with millions of qubits within the next 5 years. Here is a summary of some quantum algorithms. I highlight some important ones with their applications, for example, in cryptography, optimization, etc. They have already shown theoretical speedup or have the potential to do so. That's why we are confident that this technology can work. Seems that we already have the quantum hardware and the algorithms, but still there is no practical quantum application yet. So why is that? This figure can explain the reason. This figure shows the current status of the quantum hardware and the applications. The x-axis shows 1 over the errors, and y-axis shows the number of qubits. The current quantum hardware has around thousands of qubits, but they suffer very high errors, around 0.1%. Achieving quantum applications require many more qubits with much lower errors. So there's a gap between the capability of the quantum hardware and the resource requirements of the quantum applications. To close this gap, people are working on building better qubits or discovering more resource-friendly applications. On my side, I try to close this gap through software stack design. So I'm trying to address this question, like how can we leverage the expertise from computer science and engineering to build software tools that can help quantum computers achieve quantum advantages. My research spans 3 different areas. The first one is quantum circuit optimization. To execute an algorithm on the hardware, we need to first translate the algorithm to a quantum circuit. We optimize the quantum circuit so they can be executed on the hardware with better results. The second one is error mitigation and correction. Since quantum hardware is very noisy, besides developing better qubits, we can design some tools to mitigate and correct the errors to achieve reliable computation. So the overall goal of these two areas is to run the algorithm on the hardware with better results. So during this process, we need to keep track of the progress of algorithm and hardware. So this motivates the third area, which is benchmarking quantum algorithm and hardware. We propose benchmarking protocols and framework that can track the progress of the algorithm and hardware and evaluate how far are we from achieving the quantum advantages. So now I will talk more details of each area. First, quantum circuit optimization. For this project, the goal is to reduce the circuit size using mid-circuit measurement. It can enable to execute large circuits on small quantum hardware with high fidelity. Let's say we have a quantum application, and this is the circuit to implement this application. If this circuit is too large to run on the accessible quantum hardware with limited number of qubits, it becomes infeasible. To solve this problem, we propose circuit resizing algorithm, which can apply mid-circuit measurement and reset to reduce the number of qubits. It is based on analyzing the gate dependency graph or resynthesize the circuit based on instantiation. We obtain the resized circuits with less number of qubits, and now we can run this circuit on the quantum hardware. Apart from that, I also worked on some projects including compile the circuits to satisfy the hardware physical constraints or develop noise-aware and application-specific optimization methods that can tailor the circuits to achieve some specific goals. The second one are mitigation and correction. In this project, the goal is to develop some new error mitigation methods that can suppress decoherence and crosstalk errors to achieve high fidelity. This figure are some quantum circuits. We analyze the structure of the quantum circuits, for example, the gate parallelism, and then we evaluate the impact of the errors on these structured circuits. Based on this knowledge, we developed some error mitigation method that leverage a technique called dynamical decoupling to reduce the errors. So here's the result. For example, we can see our protocol can significantly improve the fidelity compared with the baseline. And our method almost has zero overhead. It just requires to insert some single qubit gate on specific locations, and it's also scalable to arbitrary circuits with very large number of qubits. The third one is about benchmarking quantum algorithms and systems. Here in this project, we introduce a framework that can evaluate the performance of quantum simulation results with some different optimization methods. And our framework is open source. You can find it in this GitHub. Apart from quantum simulation algorithms, it also supports more than 20 quantum algorithms. It has a modular architecture and is very easy to integrate with any other benchmarking frameworks. It also supports users to evaluate their algorithms on different simulators, including like Qiskit, QLQ, and different quantum hardware APIs. For the future works, I want to keep pushing quantum advantages through building software tools. This figure shows the architecture of a quantum system from the application to the hardware. My future interests span different levels. In the application algorithm level, I'm interested in optimizing algorithms for resource efficiency and estimating the resource usage for fault-tolerant quantum algorithms, and simulating very large quantum systems using HPC systems. In terms of quantum error mitigation and error correction, I'm focusing on the integration between QEC and QEM and developing some decoders to achieve high threshold for quantum error correction. For compiler and architecture, I'm interested in developing compilers for specific applications, quantum error correction, or distributed quantum systems. In the hardware level, I'm interested in the attack and security of the quantum system and also develop some advanced benchmarking protocols for quantum hardware. So that's it about my research. So if you're also excited about quantum computing, feel free to send me an email or come to my office. Let's have a chat and get entangled in the world of quantum computing. Thank you.